Hey everyone! Thank you so much for watching another episode of the Weaviate podcast. I'm super excited to welcome Matthew Russo, a Ph.D. student at MIT. Matthew is doing incredible work at the intersection of AI and database systems, including his recent work on SemBench, a benchmark for semantic query processing engines. I'm super excited to dive into these things. Matthew, thanks so much for joining the podcast.
Yeah, thank you for having me.
Awesome. So I think I'd love to kick it off for our audience to just kind of explain this concept of a semantic query processing engine and maybe introduce semantic operators and just sort of set the scene for this.
Yeah, totally. So in general, I think the best way that you can think of this pitch is that imagine that you have, your traditional database, which has a relational algebra. You use SQL to query it. And that gives you access to a bunch of operators under the hood, such as filters, joins, aggregates, group-bys, and so on. And just simply put, if you try to issue a SQL query over, let's say, a database that has, let's say pointers to images of cars, and you say, okay, I want to filter for every row in my database that has an image of a red car. Well, currently this is not really supported. Your traditional relational operator has no way of computing this filter, the car in the image that's linked by this column's file path has the color red. But today with LLMs, this is actually suddenly very possible. And in the past, there had been some work in the databases community to try and extend sort of the SQL relational model to include these types of image and video-based filters, text-based filters as well, by sort of putting these ML UDFs into the database. But what's really changed now with the foundation models that we have, both in terms of language models and vision models, is that they have extremely good zero-shot capability, right? So in the past, you kind of had to optimize the UDF for you probably had to train a cascade model and tune it and parameterize it so that for that one query about red cars, it would do a really good job at filtering for red cars in a way that was fast and high in terms of accuracy. But the great thing is that now that we have, these vision models, you could just ask it on one query, I want to filter for red cars. The next query could be, I want to filter for Porsche 911s. And because of sort of their general world and semantic understanding, it's possible to just build a system around these foundation and language models that is able to sort of in zero shot just answer any query that has some of these semantic operators. And so perhaps to just be very explicit, what I mean when we talk about semantic operators is you can imagine that you can specify the where clause in a SQL query, which we would say is a semantic filter, using just a natural language sentence. So, the color of the car is red. You can also specify join predicates in natural language. So I think in SemBench, one of the workloads, we have audio recordings of animal noises, as well as video taken as images, capturing where these animals are by trap recordings. And you can effectively say, I want to join every instance of audio where that audio is the same animal as in the image, right? So if you hear the elephant trumpet and you see a photo of an elephant, you hope that those two, image audio pair gets joined together. And then, in some of my past work, we've done a lot of work as well with optimizing semantic maps. So this is something that it sort of shows up in databases in the sense that you can create new columns on the fly using, traditional relational algebra and other operations. But specifically here, for instance, we can have a data set of research papers, and we can apply a semantic map over the research papers to say summarize the paper, compute sort of a summary field. And so the list goes on. There's also semantic aggregates, semantic group-bys as well, where maybe you're coming up with these groups on the fly. What are my customers' top 3 complaints about some product, right? You need some semantic understanding to figure out what are the complaint categories, and then to assign each review of some product to one of those categories. So, so these are these sort of new semantic operators. And what's the main challenge is that when you include these in a database, optimizing for LLM processing cost becomes the bottleneck. Suddenly a relational join is not a problem when you think about the fact that doing a semantic join is going to involve n times m LLM invocations. And so your cost, your latency is going to be dominated by that. And also, these semantic operators do not guarantee perfect quality. So now suddenly there's also this trade-off you have to balance between, well, maybe I'm going to try to use smaller models to implement these operators, but if I do that, I might be sacrificing result quality. So it's a very interesting space. And I've worked on our own at MIT, our own semantic query processing engine, Palimpzest, as well as its optimizer, which was a separate paper we wrote called Abacus. And SemBench is this collaboration led by folks from Cornell, Google, UTN, Bifold, TU Berlin, that is focused on trying to actually build sort of like the TPCH or TPCDS benchmark for this setting. And so I played a small part in that, but I'm happy to talk about any and all of the above.
Yeah, amazing. There's just so many cool ideas to it. I guess maybe like our journey of adding sort of the AI layer to querying databases at Weaviate is we have kind of on one end our query agent that does this kind of like text to SQL thing. It can write filters. And that's one of the biggest innovations, I think, is just natural language to the operators. And then we have something that we call the transformation agent that's kind of like the semantic map where it applies an LLM over all the data in the database. And then, but what we do is we then save the value into the database. And so I think kind of the way that you use these operators is more like ephemeral, like you're computing it on the fly, but you don't need to save it on the database. But that's just like a little, I just wanted to touch quickly on kind of like where we're at with Weaviate in respect to understanding these things. And yeah, I at first, I was following Liana Patel's work after she had come on the podcast, met her, and we talked about Acorn, and that's how I kind of became introduced to Lotus, and that's how I started to see this concept developing. And so I think maybe if we could just kind of talk about the semantic operators and like just, I know that you just gave a really great overview, but if we could just maybe even slow it down. I know in the SemBench you present these 5 operators of, semantic filter, semantic join, semantic classify, semantic map, and semantic rank. I think I remembered all 5 of them in the paper. But so maybe if we could just, I think if we could maybe just go further into those 5 and maybe explain how they differ. Particularly for me, I'm having a hard time understanding how semantic filter, semantic map, and semantic classifier really, they seem kind of similar to me.
Yeah. I think so. To some extent, I think this was an effort by the paper authors to try to identify because each of these systems has kind of adopted its own language of semantic operators, right? This is very early days. And so we're all trying to figure out what is the space of operators. There's one view, which I guess you could call like the semantic map maximalist view, which says that with a semantic map, you can do all of semantic map, semantic filter, semantic classify, and semantic rank, right? Like actually that one I guess is slightly different because it depends how you implement it. If you are taking an entire data set and then saying, I want to rank all the items in this data set, then it's a bit more like an aggregate operation. But if you were to first flatten, things into a row with the list, you could, in theory, use a map to just for that one row rank the items in the list. So I do think that, to your point, a lot of them on the surface as a programmer, you might say, oh, I could potentially implement both filter, classify, or rank using a map operator. I think that the key distinction and what's really important here, and I'll highlight this especially for map and filter because I think this is where it's most obvious, is that by explicitly separating, a filter from a map, you actually enable a different set of optimizations under the hood that the semantic query processing engine can go and implement on the user's behalf. And I think that, for database folks who are hearing this, this is kind of obvious. For AI folks who maybe don't think about declarative optimization so much, this might be like a little bit of a weird paradigm shift. And so for like a 30-second overview of declarative optimization, the real pitch is that, in a database system or in a semantic query processing engine, you don't tell the system how it should implement an instruction, right? So if you say, I want to apply a semantic map to extract the summary of a set of research papers. Extracting the summary for each paper in that data set, you don't say like, you should do it using GPT-4o mini with this temperature setting. You don't say, oh, you should do it by using an ensemble of these 3 models and then synthesizing their summary into one more concise one. You just say, I want to do a semantic map. This is the instruction, go compute a summary, and the system is left to optimize that itself. And so you're putting your faith in the system to be able to take that high-level instruction, to compile it down to some physical execution that ideally is going to give you really high quality, really low cost, and really low latency. And so because of this, for semantic filter in particular, one way that a lot of these systems have optimized these filters, and I know this is true of Lotus, and I think Thalamus DB, they also use approximate query processing techniques, so they may also be doing something somewhat similar. But in Lotus, what you effectively do is you have, let's say, your gold algorithm, which could just be like applying the most expensive model to all of the records in the data set to compute that filter. And then you can have a proxy model, which is like a much cheaper and faster version of it. So that proxy model, instead of, let's say, being GPT-5, it could be like Llama, 3 8 billion parameter model. And what they will effectively try to do for that filter operation is that they'll apply the Oracle model, the powerful model, to a bunch of records. They'll then compute certain thresholds where it's like, okay, anything above this threshold for they'll also run the proxy model on the same set. So they get sort of like a sense of like the proxy's confidence as well as the Oracle's confidence on how well each record passes the filter. And then based on sort of by looking at the result from the Oracle and looking at the scores from the proxy, they can kind of set these thresholds where it's like, okay, if the proxy says something likely passes the filter with a score above like 0.7, let's just say, we're automatically going to just let that pass the filter. We don't need to run it by the Oracle. If it's below some low threshold, we're going to say, okay, it's automatically not going to be processed by the filter. And then maybe if it's in some small band between the low and high threshold, then we say, okay, it's really unclear. So only these small band of records will go to the Oracle. And so in doing that, you effectively trade off potentially a little bit of accuracy by not using the Oracle for every record, but you save hopefully a lot in terms of processing cost and processing speed. The thing is that you can do that for a filter because it's very easy to assess the binary like correctness of the proxy and whether it agrees with the Oracle. Like both of them said that this record passes the filter, or both of them said that this record does not pass the filter. With a semantic map where you're computing the summary of a research paper, you can't really do this. I can't take like the Oracle summary and the proxy summary and come up with some notion of like, oh, like, okay, in this setting, I can use that. So that's to tie it all the way back to your question. That is why it's actually kind of important to have this distinction between a map and a filter, because the nuance of those operations allows for a different set of optimizations under the hood. And there's similar sort of things you can do with ranks and classify operators as well. So I think that that's kind of why we split out the set of operators in this way.
Oh, that's very cool. Yeah, there's so many cool things to that. I mean, yeah, the kind of declarative programming model is always so exciting. I'm a huge DSPy fan, so I love kind of thinking about it in that sense. And yeah, so I guess like with the operators, yeah, I think that's a really great explanation of how semantic classify and semantic map, semantic filter differ for the query engine. And then I kind of just, as listening to you talk, it's inspiring me thinking about these kind of database query planners, the kind of cost models, as you mentioned, the proxy model and the Oracle model. And so maybe we could introduce this concept and then later come back to semantic joins, because I think that is such an interesting, different concept. But this kind of like in relational algebra, say you have two filters, the car is red or the car is a BMW, there's like an order to which filter you should apply first. And so as far as I understand it, that's kind of the general setup is there's like an optimal ordering to how to apply the filters. And then maybe in Abacus, you have something like a sample 500, start running the filter in order to get the, to even have a sense of what the cardinality of the resulting filters might be. I can maybe just mind explaining that sort of like what a query cost planning model is. And yeah.
Totally. So I think that this is one of the strengths of our work on Abacus. It's something that we emphasize a lot. This is one distinction, I guess, between Lotus and Palimpzest and Abacus, which I'll just refer to that as either Abacus or PZ when talking about my work. The name Palimpzest is kind of a mouthful. But so Lotus uses like the data frame processing model. And so actually it cannot do sort of like the filter reordering, like you mentioned. And that's just because depending on the order and because it's not a lazy execution model, it means that for each line in your program, right, if you have your data frame and you do data frame.filter, the car is red, and that returns a new data frame. And then you do data frame 2 is equal to data frame.filter, the car is a BMW. The problem is you have to materialize that first data frame that filters for the car is red before you can process the line that says the car also is a BMW. And so in Lotus, you can't reorder those filters. But in a system like Palimpzest, and I believe it as well, like in BigQuery and ThalamusDB, these have a lazier execution model or just a traditional SQL model. So you submit basically the whole query, and then what will happen is that underneath the hood, there's a query optimizer, which will take that query and then apply any set of, at least in Abacus, transformation and implementation rules. And so transformation rules include just like logical reorders to the plan. So that could include reordering filters. It also, in theory, could include reordering joins, although we haven't written that optimization into our system yet. And then it also includes what we call implementation rules. And so that's like saying, I'm going to execute this filter with GPT-5, or I'm going to execute this filter with Gemini 2.5 Flash. So the implementation rules are kind of where you get your map or filter specific optimization of like which model to use, or should I use an ensemble, things like that. And then each of these systems to some extent will have a cost model, which tries to effectively provide a prediction. And it can be either, in our case, it's based on sampling, but we try to get some notion for each operator of, if we implement it this way versus that way, what do we expect the cost per input is going to be? What is going to be the latency per input? And at least in our system, on a scale of 0 to 1, how high quality is this operator going to perform for this specific map, filter, or classify operation? And then basically it's a dynamic programming algorithm that will go through all of the possible configurations of the physical plan, considering possible reorderings of the filters in the logical plan. And then it basically tries to return the physical plan and execute that one that is optimal for your user objective. And that last part is also one distinction for our system is in PZ and Abacus. Users can specify if they want to maximize quality, if they want to minimize cost, if they want to minimize latency, and they can also apply constraints to the other dimensions. So you can actually say, for this query, I want to optimize for quality, but I don't want to spend more than like 10 cents per input record. And so that kind of gives you a little bit more control as a developer over, like, if you're prototyping at first, you can just go for like the min cost optimization until you get your query working. And then over time, you can try and play around with like maximizing quality, but maybe with some thresholds on cost to keep it more manageable.
I'd love to ask about how you think about with Palimpzest the design of so does this layer live as like a service outside of the database, or would this be something that's built directly into the database?
Yeah, I think so. We build it as a framework in Python, and we made that choice mainly because we were just like, this is where the AI folks are. This is very AI driven. At the time that we initially published the Palimpzest paper, there were not many of these SQPs kind of around. I don't even think this sort of formalization had materialized yet. And so it was sort of like we wanted to do this outside of the database because we weren't sure whether it was really going to work that well. And it seemed like implementing this in a database was going to be a lot of overhead and a lot of software engineering effort. So we implemented it outside so we could kind of have full control over the system, the optimizations. But I think that that all of the ideas in PZ and Abacus can be directly applied to a database. So you could in theory apply this cost model or some of these optimizations into and I mean, Google's kind of proof of this in the SemBench paper, right? They have BigQuery, which has these semantic operators built into the system. So I think that you can definitely, like PZ itself, I wouldn't say as a database, but you can do many of the same operations in PZ. And then if you were working at, a database company, but you wanted to borrow ideas from PZ, you wouldn't use PZ per se itself, but you would probably lift those ideas and then implement them in your database.
Oh yeah, that's super cool. And so I'm sorry if this is a dumb question, but I don't really understand the kind of query planning that well. But when you mentioned like the physical plan and the logical plan, I'm curious, like does the physical plan, like when you're building Palimpzest on top of a database, like say Weaviate or or like Postgres or whatever it is, can you get some kind of API to see like physically where is the data? Or is that what's meant by physical plan? Like there is some here's exactly how on disk the data is, and these are the indexes. Or, yeah.
Kind of, yeah. It's inspired a lot by what you're saying, which is that the logical plan is sort of just the representation of your query, where you just have the types of the operators, right? So you can imagine. Let's take as an example. I think we have this diagram in our Abacus paper. There's a set of research papers, and you want to filter for papers that are about databases, and then you want to use a first semantic map to summarize the main contributions of each paper. And then you want to use a second semantic map to classify whether they're relevant to your interests. And you can specify what your interests are in the map instruction. All right. So there is a logical representation of that plan, which we would say is it's a scan, because you're going to scan over all the research papers. And then it's a filter, so because you're going to apply your filter, and then it's two logical maps. And so that logical plan can be optimized in essence by making sure that the filter happens before the maps. You could imagine someone could have written the same program where they did the two map operations, and then the last step was to filter about this is about data systems, right? So logical optimizations for the logical plan correspond to things like, oh, I'm going to push the filter down so that we execute that first. It can include, if you have semantic joins, the order in which we execute these joins, depending on what we think the cardinality of the join might be. And then the physical optimization in a logical plan, you still don't have this notion of like, how am I going to execute the map? Like, what model is actually going to do this task? And so that's the difference between a logical and a physical plan. A physical plan is just saying like, okay, it's the logical plan where the filter comes first. It's a scan, filter, map. And specifically, we're going to do the first filter with 8 billion parameter model. And then the second map with GPT-4o mini. And the final map is going to be like some ensemble that uses these three models. So that's the key distinction. But to your point, in traditional databases, a lot of that difference between logical and physical is that the physical plan depends a lot on understanding like where is data laid out. That's going to tell you things like and like what indices do I have available to me. That can give you a sense of like, okay, what's the cheapest scan option for this query? So you're definitely barking up the right tree.
Awesome. Yeah, well, it's super interesting. Yeah, it's such a cool topic. I guess maybe just kind of before diving a little further into the systems and how particularly they optimize them and design these, especially talking about the selecting the models. I'm really excited to dive into that, but also just maybe want to set the stage for our listeners more on semantic joins. I'd seen this article really early on, like here's like maybe an application of vector searching would be like it'd be like dating, and so you'd have like the two pools, and you'd be yeah. Do you mind maybe just telling the story of semantic joins?
Yeah. So semantic joins, I think there's a lot of interest in them and excitement around them, in part because in traditional databases, optimizing joins has been extremely important for getting good query performance. And I think that I'm actually going to maybe I'm going to be a bit of a letdown here. I'm going to give you a bit of a pro and a con here. So the pro is that the same should be true in the setting for semantic operators, where if you have a query with a semantic join, that is going to dominate the cost of the query. Actually in the revision for Abacus, we just had to rewrite one of our programs to have 3 semantic joins, and one of these semantic joins involves like 12,000 images, and so the query costs like anywhere from $2 to $27, depending on how you physically implement, the matching of images to text strings. And it just shows you like how important it is to if you're trying to minimize cost, like use the cheaper embedding based approach to join these things. Cause like if you run a vision model on 12,000 images, you're going to spend quite a lot of money. So I think that from an academic perspective, there's a lot of excitement around how do we optimize these joins. You can think of potentially another technique as being like let's just say you wanted to join two different pairs of text. So maybe it's like movie titles and then descriptions of the movie. Like, is this, or genres perhaps. So for each movie you want to match, does it correspond to a certain genre? You don't necessarily have to, take, let's say you have 5 movies and 5 genres. You could process them one by one. So you could take the first movie and the first genre and ask, does the genre match the movie, true or false? And you could kind of then go down to the next genre and so on. Alternatively, you could also just take all 5 of them, feed them into the LLM as a batch, and then ask it to come up with a very compressed output that tells you only the movies that join to certain genres. And so you would save on the number of LLM calls, which hopefully reduces your latency. And also, you could potentially save on some processing costs if you're clever about how you elicit the output from the model. So for these reasons, like, there's a lot of excitement around, we've had all these ideas and we've spent a lot of time optimizing joins in relational databases. Clearly, there's a lot of work and research to be done optimizing these joins for the semantic setting. So that's my bull case. My bear case for semantic joins is that it's actually kind of hard to come up with. It's not impossible, but it actually takes racking your brain a little bit sometimes to come up with interesting examples of semantic joins that are extremely relevant for data processing workloads. And maybe it's less true for text to text. But like for image to text, even it can be slightly difficult. Like, you might think of like, oh, does this caption match the image? Okay, that makes sense, right? Yeah, like, does this caption describe what's happening in the image? Totally get it. But like, what's an example of a setting where I have a bunch of captions and a bunch of images, but they're separated and I need to bring them together? Like, usually the two come together already. So I would say that, and I'll probably like be proven wrong in 1 year, and there'll be like a lot of egg on my face for this take, and people will be like doing tons of examples and like, here's an obvious semantic join. Um, but at least that's one thing where sometimes when I tell folks about this, one feedback that I've gotten from like non AI experts in the past has been sort of like, okay, but like, when am I going to actually do that? Or why wouldn't I just, apply a filter on both sides, extract some distinct field, and then do a relational join? And that is potentially an optimization also that's worth looking into, is like, and that you could implement as an optimization for a semantic join in a system, would be to say, like, we actually do a filter and a map on both sides, do a map on both sides to extract like what animal is in this image, what animal is in this audio snippet, and then just join on those those animals in a relational fashion. There are some downsides to it. We actually did kind of try this for the animal image query. The problem is that sometimes on the map, if you don't like distinctly say like these are the classes for the animals, you can get one that's like, this is an image of an elephant, and then you can get an audio recording that like, that's the audio of a North African elephant. And then when you try to join elephant to North African elephant, it doesn't join if you do it in a relational fashion. So it's a tricky subject for sure. But I think it's one that's very exciting. And I'm sure in a few years' time, we'll have tons of use cases and I'll look like a fool for my skepticism. But yeah.
And it inspires me to think of one of those GitHub repositories. It's like awesome semantic joins, and it's just like a collection of like thousands of queries like this. I can imagine like the job applications to resumes one is like a good motivating example. I do think the dating one is pretty good. I mean, we do have like a customer at Weaviate that uses vector databases for that kind of thing.
I think it's definitely, to your point, text to text. I think there's a lot of examples. Another one I've heard about is there's a company that does sort of like Mechanical Turk, right? Like, people submit tasks and then there are sort of workers with certain skills. And so they're actually trying to use, from what I understand, AI to try and match, qualified people to perform given freelance tasks. But again, the multimodality aspect, I think, is where it's kind of hard. It's like, where do audio come into this? And so it may end up being the case. But even still, like, if you have a lot of text things you need to join, it's good if you can do it in an optimized fashion.
Yeah, it starts me to maybe think of joining like images with like music. Oh, yeah, that's cool.
Yeah, it's like you see, it's a little tougher to come up with one and like convince yourself like, oh yes, this is needed. But I'm sure that there are use cases. I just it's hard when you're in your bubble in academia sometimes to think of these things. But there are definitely folks in industry who are like, what are you talking about? Like I have to do this every day.
Yeah, it really, I mean, I love kind of setting the scene with like the declarative programming model, and it's like how particularly we implement the semantic joins is indifferent from just defining it as one of the operators. But it makes me think like it could be like either extreme multi-label classification to try to map these two things to each other. Like if I have 100 unique categories of the one thing I'm trying to join with the other, it's like that problem.
Right.
And then I really love topic modeling. Topic modeling where you're like clustering the vectors. You represent which objects with vectors, then you cluster them, and then you summarize the clusters. And maybe that has something because you're kind of like coming up with the categories on the fly. I don't know if that's quite a semantic join. I think that's like a
I
some
think
op. Yeah,
like a semantic group by potentially
yeah,
could be an instance of that. And the cool thing there is that actually what you just described would be a semantic group by where the aggregation is also semantic. So you're clustering the groups and then you're saying, okay, what does this group represent? Like come up with a semantic description of it. And I think that that is actually a very, very interesting problem because a lot of traditional like clustering work that's kind of what you're trying to do. It's like if you have a bunch of unstructured data and you're just embedding it, clustering it, and then hoping that these clusters mean something. In theory, there's a world in which we have you just say, I want to do my semantic group by, and the system can optimize it, and then you just can, ideally have some levers of optimization to try and maybe get those clusters and groups to align better with what you are expecting in the data. So it, in theory, could make that whole like embedding based clustering problem a lot more streamlined.
that also like at opening the podcast, I mentioned that at Weaviate we have this thing called a transformation agent that's kind of like semantic map or semantic classify, where we save the attributes back into the database. And something we saw people do a lot is they'd run the transformation agent and then they'd use the query agent to ask questions about this new property. Like if you're saying the car is red and you didn't already have that stored. And so then with this kind of semantic group by, I was thinking like about like Databricks has this catalog. They call it Unity catalog, sorry, where it's like about cataloging data. And I thought that could be a really great like interface for this semantic group by is like kind of like a catalog agent. And Weaviate is like something that would group your data, give you a nice way to visualize these groups. Yeah. Anyway, so it's just so cool. So I'd love to. I think this would transition well into talking about the data set because we kind of talked about like these use cases examples of semantic joins. I think kind of maybe yeah, if we could now kind of transition into talking about what SemBench is and yeah, how you're trying to benchmark these.
Yeah. So I think that at a high level, the goal for SemBench is to kind of create a parallel to your TPCH or TPCDS uh, benchmark, which for analytical query processing has kind of been like the gold standard for testing out different databases, different query engines, query optimizations. And so the key problem with those benchmarks is just that they don't have text or like large text fields or images or audio. And so in this new domain where we have semantic operators and where cost, latency, and now variable quality are determined by the LLMs you use and how you apply them, it really requires a new benchmark so that we can test out systems and get a sense of, you know, um, which systems perform well at what operators. Are there certain types of queries that are difficult across all systems, or where do we see high variance? What optimizations work well for this setting? So I think that the initial SemBench paper, again, very large collaboration of which I played a small part. So I want to give credit to all the other authors on the paper, and I don't want to speak for all of them, but just at least my perspective on the benchmark. And I think that it's a great addition to the space. We've already been able to benchmark Lotus, ThalamusDB, Palimpzest, and BigQuery in this setting and create a leaderboard that's public. So people can kind of investigate the results and play around with these different systems. And I think that there's probably a future where we're going to continue to grow and expand the benchmark as well. Because right now it has 55 queries across 5 different workloads. And so those workloads, we call them like movie, wildlife, e-commerce, MMQA, and medical. And they span effectively queries over 4 data modalities: tabular data, text data, image, and audio. And they include all of the semantic operators that you just described. They're not semantic group by and semantic aggregate, but also that's something that I think maybe in the future we would look to include in the benchmark. Just my perspective, again, not speaking for everyone else. So I think that the benchmark is great because for a while, when we were writing both the Palimpzest and the Abacus paper, we were you kind of had to just like find data sets that had been used in other AI settings and papers and workloads, and usually you couldn't even use the task as it was described, so you had to kind of change it a little bit to make it fit really nicely into like, oh, this is actually a filter with a map, and then maybe you can add a second filter somehow, so now we have to be good at figuring out the right ordering of filters. Or maybe I can represent this as a semantic join, and so now join reordering becomes a problem. But there just like wasn't a clear and clean benchmark on which to say, okay, we're all going to evaluate on this. We're going to have some agreement about what are the settings and what are the parameters for the different systems under evaluation, and get sort of a very clear understanding of which systems are good at which operations, and how do they perform relative to one another. But I think that honestly, the relative performance is not that important, because again, it's very early. These systems are still very sensitive also to prompts, and so you can get very large performance changes just based on changing the prompt, which ideally in the future you would normalize for that. But yeah, I think it's a step in the right direction, and it's hopefully the type of thing where when you build the right benchmark, a whole community can build up around that, and sort of drive performance and drive research into this area.
Yeah, it's so cool. I think like database benchmarks is such like an evolving area. Like as I mentioned, when we were building this kind of like text to SQL thing, we saw these data sets like Bird, Spider, Wiki SQL, but then we're like, well, we want to add a search query operator to it because they don't include that in the SQL language. And I can imagine adding all these semantic operators. And yeah, so you designed this data set using Kaggle, is that right? Like, how do you?
Yeah, so I think a lot of so for my part, I didn't do a lot of the query and benchmark creation. I was mostly responsible for just making sure that like the PZ queries were implemented correctly, helping support with bugs that came up in that sense. But my understanding is that for most of the scenarios, what happened was they took publicly available Kaggle benchmarks or Kaggle datasets. And then what they did was they created sort of 10 queries over those datasets. So I think the animal one is actually a really useful example. I actually think it was originally 2 separate data sets. I don't quote me on this, but I believe it was 2 separate data sets, one that had animal recordings and one that had images of animals, but they both had labels of which animal was in the recording or in the image. And so what we were able to do was basically to construct a data set where we said, okay, we know the ground truth for what this recording should be in terms of the animal. We know the ground truth of what the image should be, and then we also generated some tabular data about like the location where, and this was like generated at random, somewhat like the location of the image and the location of the recording. But then what that enables you to do is you can suddenly construct SQL queries that are like like which location has the highest number of elephant images. And so that requires filtering over the images, but it also requires implementing an aggregation, a max operator over the output. So we were able to effectively construct these queries by taking existing Kaggle datasets. And the key reason we used Kaggle datasets was because they already had ground truth labels. So we have ground truth for all of the queries in the benchmark. And that allows us to sort of fairly accurately assess, what is the quality of a given operator. I think one limitation of this approach, or something that we'll have to explore in the future, is for something like a semantic map where you're trying to compute a summary. Again, it would be and maybe the answer is just that we don't do that in the benchmark. Like if we do extraction of information, it has to be like very well defined and in a rigid sort of field. So extracting like the authors of a paper, like that's we can very easily assess whether you did that correctly or not. But I do think that there are, anytime you're using LLMs, evaluating accuracy and quality is a challenge. And in other settings, we've seen LLM judges be used, but it remains to be seen what we might do for semantic operations that have less tangible outputs, something like a summary where it's harder to quantify.
Yeah, mentioning adding the synthetic tabular data about the locations really reminds me of like I mentioned kind of how I met Liana and sort of like just through the path of all these things became aware of the semantic operators. But we're researching filtered vector search, like vector searching with filters, and there's not a good data set that like has a filter. So what we were doing is we would just do like mod 10 as we're inserting the data into Weaviate, and that's your filter, like 1, 2, 3, and then what we found is that there's actually, it makes sense in hindsight because like the filter, and then the vector embedding correlation. But we found that there's like a correlation between the filter and the vector embedding that impacts the filtered vector search. So it's just like trying to construct these benchmarks that like combine unstructured and structured. It's like, I think, quite an unsolved problem. Yeah.
Yeah, it's very time consuming. It's challenging work, but it needs to be done. And so I think that for people to publish, like I think that publishing benchmark papers is a great direction for communities right now because, like you said, even for sort of hybrid vector search, we need to have really good authoritative, not it shouldn't be the end all be all, but you definitely do want to have some sort of benchmark that everyone can kind of evaluate and get a sense of like, well, how well does my system perform? Where do I need to invest more energy and time to make my system better? So yeah, I totally agree.
Yes, and so I think kind of this is related. You mentioned kind of like the TPC benchmark, and this is something I really wanted to get your opinion on. Is the sort of interaction between semantic operators and then like difficult relational operators. So like, and kind of earlier I mentioned asking about like Palimpzest being built on top of other databases, and I'm curious, like say like ClickHouse is a database that's optimized for these like really fast analytical queries. And so I'm kind of, because like the and you mentioned separating the logical from the physical, but like certain databases implement certain non-semantic operators faster. How does that kind of interaction? Uh,
Yeah. So I think that the truthfully right now for most of the systems and for most queries, you're if all you do is focus on optimizing the semantic part, you're going to do great. like such a because the order of magnitude difference in processing time and cost is so large. Even in a hybrid query where you do have a mix of relational and semantic operators, if all you really if your optimizer primarily focuses on just the semantic portion, then you definitely can win on a lot of queries. That being said, you are 100% right. It is not impossible to construct data sets with, let's say, millions of records, where potentially if you do the right thing on the relational side, you actually then only have to process very few semantic operators. And so you actually perhaps the amount of compute that goes into doing some relational join or relational filter is so high that it actually requires a intelligent optimization on the database side as well. And so I think that I don't have a good answer for you right now about like what do the different systems do for this. I think most of them, BigQuery, I would assume would probably be the most ahead right now because they've optimized for relational queries for a very long time, and so they probably still have access to those optimizations even when they're using their AI enabled semantic operators. But yeah, in Palimpzest, at least I can say we don't do anything special for the relational portion. But in the future, if we have one thing that I know we've talked about is adding indices into the system, both in a semantic and non-semantic variety. So in theory, if you had an index over some relational data, we could leverage that instead of just doing some line scan or something like that. Yeah.
yeah, I guess like quickly talking about that, like I think something we saw with like Weaviate is people would build a lot of RAG systems where, yeah, the vector search it might be only 10 milliseconds, and that's great, but the LM is 5 seconds, so it's like you save me 90 milliseconds, but
Yeah, that's just the nature of it. And I think so one thing that I also am somewhat bullish on is that the processing cost and times are coming down. You have, obviously in the news, massive AI data centers being built, possibly propping up the entire US economy at this moment in time. So this is a massive level of investment. And I think that everyone is hoping that 3 to 4 years from now, compute is going to be so widely available that it may not be crazy to say that if I have a semantic filter, I could run 10,000 LLM operations in parallel, right? So, right now you're somewhat limited by like the API rate limit and how many filter tasks you can fire off to some service provider, or if your system is managing models on local hardware, right? It's like how many GPUs do you have? If the supply of GPUs goes up in both of those settings, then ideally we can parallelize these requests a lot more. And then so in that sense, the latency on the semantic side would hopefully come down quite a bit. So, again, in this very straw man example of like I have 10,000 filters I want to do, if I have 10,000 invocations that I can do in parallel, well, suddenly now at the time of this, just the time for one, like the max length LLM call in that batch. And perhaps then, your relational operators become much closer in terms of scale, order of magnitude, in terms of time. So I think definitely in the not too distant future, you could see these things start to approach one another. But right now, GPUs are still somewhat scarce. And so that dominates the bottleneck in computing these queries.
Yeah, I think that's such a cool one. I don't mean to be plugging Weaviate things like every conversation turn, but
Great.
just like what my intuition is thinking. But like we do that, and I'll give a shout out to Modal. We use Modal has like really great 0 to, I don't know about affinity, but like 0 to tons of GPUs, and then that's how we do that like batch updating and that kind of thing. Yeah, definitely a big time. I think like kind of like co-locating data in compute is a very interesting topic with this.
I would,
But
yeah. Given infinite time, I would love to spend. So Palimpzest right now and Abacus, we mostly just support. We have very, very basic support for VLLM. So if you want to run, like a local model SM server, but effectively all of the optimizations are not leveraging like the system itself is controlling the model weights. And so we can do some fancy tricks there. That's 100% a great direction for future research, but something that is not currently in Palimpzest. But I think that there's a ton of room to explore how you could optimize in that setting. But yeah, we mostly focus kind of just on the API based processing.
yeah, because you could have like a 5 millisecond database index, but then a 50 millisecond network latency. So it's like, and then you gotta co-locate the pods and the zones and all that stuff. So I really wanted to just sort of maybe anchor with. I don't know too much about the systems and the optimizations behind them, but maybe if you could just explain Palimpzest further, kind of like the landscape between Lotus and the Almas DB and BigQuery again, and then just sort of like what exciting directions are sort of on the roadmap for Palimpzest.
Yeah, totally. So on the Palimpsest side of things, as I mentioned, we support most of the semantic operators, all of the ones in SemBench, as well as a few others. And the primary means of optimization are that for maps and filters, we sort of have 4 different optimizations. The first one is model selection. So which model am I going to use to implement this map or filter? The second one is we call it mixture of agents. It's effectively an ensemble. So you ask a bunch of what we call proposers to generate, the map output or the filter decision. And then there is an aggregator which takes all of the proposers' outputs and then synthesizes them into sort of one final either filter decision or map output. There is a critique and refine operator where an initial model proposes an answer, a second model then critiques the answer, and a third one produces the refined output. And then the final optimization we have is sort of, we call it like context reduction. And so for that one, the simplest example is like if you want to compute a summary of a paper's main contributions, you don't need to read all 12 pages of the paper. You can usually just read the introduction. And you should ideally get, if the paper authors did their job, from just the introduction, you can get a summary of the main contributions. And so in the context reduction optimization, what we will do for filters and maps is we'll actually first chunk the input, embed each chunk, take the embedding similarity with the map instruction or the filter instruction, and then take some top K number of chunks or embeddings and only filter the map, apply the map or filter using just those chunks. And we'll use like ... to connect the chunks. And so out of everything I just described, model selection offers Palimpzest and Abacus a way to explore the trade-off between latency, cost, and quality just on that thin Pareto frontier of like, which model you decide to use. The mixture of agents and the critique and refine are pretty much exclusively relative to model selection going to increase your cost, right? So now instead of using one model, we're using 3 in the critique and refine and using some number of proposers and an aggregator in the ensemble. But what we do observe is that for large document processing tasks, you do get better performance as well. So in our Abacus paper, there is a task around like extracting patients' reactions to drugs from these medical reports that describe, a patient took XYZ drug and then they had this adverse reaction. And so in that setting, as well as in this other legal contract understanding benchmark called Quad, if you use these ensembles or these critique and refine loops, you can actually get higher quality. Again, though, at the trade-off of higher costs and higher latency. And then the context reduction one is primarily geared towards saving you on cost and on latency. So if you have a large input document, by chunking it and only processing your map or filter with the most relevant chunks, we can potentially save a significant amount of input token processing, by ignoring most of the irrelevant portions of the document. So that's on the filter and map side. We have a top K operator, which is sort of like we effectively will retrieve the top K objects from some vector database based on their relevance to some natural language text string. And so we can optimize for the value K of how many objects do you want returned. So effectively, you can think of it as like if you have some pipeline that's doing some sort of RAG operation, we can potentially optimize the value K for what you return. And, ideally, small K is going to give you obviously fewer items, but also could avoid cluttering the context. So it's a little less clean in terms of like, is it saving you on cost? Is it improving on quality? But the nice thing is that we at least give the optimizer the ability to try and figure out like what's the optimal value of K for your task and your workload. And then the final one is Semantic Joins. And so we offer the naive nested loops join, which is just take every pair of items and run an LLM. But we also have an embedding-based approach in which we compute a embedding for every item, and then we use, again, like an Oracle model on some subset of the data to come up with that high and low threshold. And then for the rest of the query, anything where the embedding pair similarity is above the high threshold, we automatically join it. Below the low threshold, we filter it out. And if it's in that middle band, then we still use the Oracle. So that's like sort of the overview landscape of optimizations in Palimpzest and Abacus. And the way that the system actually determines which optimizations to apply is that there's like sort of a fixed sample budget, which can be specified in dollar cost now. So you can say like, I'll spend, $1 on LLM calls to try out a bunch of these different techniques. And we have some like clever algorithms around trying to pick promising operators and then continue to sample those operators to get better and better estimates about their performance. And then once the sampling budget is exhausted, then we do that sort of, as I was saying, like that logical to physical plan construction, generating a very large space of physical plans using all the operators that we sampled and all the different approaches to implementing the map, the filter, the join, top K, and then returning sort of the Pareto optimal plan for the user's objective. So that's, and usually when I say that there's like a very nice slide behind me that I can like click to and point at. So I don't know how well that comes across if I just say it out loud. But feel like if you have any questions about that, please ask me so I can help clarify.
Yeah, it's so cool. So many exciting ideas, which is hard to even pick a question because there's so many cool things to explore. But I guess I had a quick question about like sort of the implementation of semantic filtering or classifying, like, is that like it could just be an LLM inference, or it could itself be a RAG inference, or I guess it could be like an agentic inference, where you use like a function calling loop and it's got tools to implement like each of the calls.
Yeah.
Is that what you, yeah.
Yeah, I mean, like this potential space of, and I think part of what drove our interest in this direction that we took for Abacus was that we imagined that the space of optimizations is insanely large. And some of the other semantic query processing engines, again, and this is our difference because this is sort of our very biased view of the way that these engines should work. So naturally, this means that our system, like this is the line on which they differ from others. In a lot of other systems, there's sort of this bias put on the in terms of the people who wrote the system, where they say like there's a certain goal, which is like we're going to try to preserve the quality of some model, but potentially save cost by using like a proxy to process some amount of the data. But what that really kind of restricts the system to is like it can only optimize for saving on cost and quality relative to some oracle. And if that oracle is not great, then you're kind of like there's not really much that you can do in the system internally to optimize and make the query better. Um, and one thing that we wanted in Abacus was to admit as the largest space as possible of these types of optimizations and provide effectively an interface in which developers can write new optimizations. And by design, our optimizer treats each optimization as a black box. That's why it has to sort of sample them to get an estimate of how well they perform. But because of this, basically what that means is that as long as you, like, let's say that you decide that we should try doing semantic filtering by first doing RAG to look up, like, embed everything that you're going to filter over. Use RAG to get the top k equal to 100, and maybe k is a hyperparameter so it can be scaled. And then you only process like those k items with the LLM. And that optimization, again, the lever is that value of k. So, like, if k is 1, it's a super cheap operation, but it probably misses a lot of important things. If K is the entire data set, well, then you're just running an LLM on everything at the end of the day. So it's super expensive. But you can tune this K parameter to kind of trade off between costs and hopefully accuracy. You can go write that in a class. You just have to implement two functions. You can then plug it into Palimpzest, and Abacus will basically be able to optimize over it. Again, because it sort of treats every optimization as a black box that has to be sampled in order to assess its quality, its cost, and its latency. So we definitely believe that this admits a lot of fancy optimizations. Like in theory, you could even have an optimization where the optimization is literally like an agent will write Python code and then apply that Python code to do the filter operation. And perhaps in the Python code, it's invoking like some Hugging Face model, or if it's like simple enough of a filter, it can just be implemented with a regular expression or other like string matching logic. That's also possible. And then the great thing there is like you write the function once, that's one LLM call, but then you apply the function to the rest of the data set, so you save a ton on your cost. And that's sort of the key like biased perspective for the Palimpsest and Abacus system is like you could go and write that optimization today, plug it into our system, and it would work. And so we're not being prescriptive about like what optimizations should exist in the system. We're not curating that. We're admitting the widest possible space and then saying that we're going to try, and our secret sauce is like, can we search over a massive space of these optimizations and find ones which are good for your query?
Yeah, that's so cool. And so I was maybe thinking about like kind of the integration of DSPy, where you might submit a prompt for like one of these tasks, and then you optimize that prompt with Gepa as one of the optimizations you're exploring in parallel. And yeah, it's really amazing. And then the systems thing, mentioning like each of the inferences is a RAG inference. Now you maybe have this like batch query workload. And it's kind of something like when we were working with NVIDIA, they have like the Cagra vector index for like running on GPUs. And so it's like, it's really particularly really good at building the proximity graph really quickly and then batch queries. And so I just always kind of been thinking now about like, oh, what is the application of like batch queries? And maybe this is that example because you're about to run 100,000 RAG inferences.
Yeah.
or
Right.
more.
Yeah. So it's but it's an exciting space, and I think and that's one of the key things is that the space of optimizations, because AI development happens so quickly, it's just going to grow and grow. And so we're we're designing to try and be flexible to admit new optimizations and new techniques as we get more great new papers about all these different AI processing techniques.
Yeah, amazing. Well, Matthew, thanks so much for joining the Weaviate podcast. I've learned so much about semantic query processing engines, and all these things are just so exciting. One sort of anchoring question I like to ask, just maybe like broadly outside of your particular expertise in this work, is just sort of like what future directions for AI excite you the most? Like what kind of gets you out of bed in the morning, think about AI?
Yeah, I think I guess one very succinct one for me is deep research, and so I've been really because at a very high level, deep research actually looks a lot like a declarative database processing system. Like users give very high level intent. The system then has to take that intent, come up with some plan for how it's going to, answer the question that the user provided or do the task that the user wants it to do. And then, after 20 or 30 minutes, I think for current systems, like maybe less time, but the system will come back with your final output. But that maps very closely to this declarative world in which you say, like, the user doesn't tell the deep research agent, these are the steps you have to follow. They just say, like, here's some Excel spreadsheets, like come up with a financial model for investing in Fortune 500 companies or something like that. Or like, we hope students don't do this, but I am sure students have done this. Like, here's a chapter of my textbook, like generate the study plan for me. And so, what users care about is like, I have this instruction, I want the output, and it's up to the system to optimize, like, how do you go from instruction to output? So I'm excited by that because I think that it maps pretty closely to this space, and it remains to be seen what's going to be the overlap or the parallels between semantic query processing engines and deep research.
Yeah, I think maybe the generate a study plan for the student isn't such a is such a bad use case of it.
It's definitely in demand. I can say that.
But like the get my tweet, get this 1 million impressions, whatever you have to do, or
Yeah, the opportunities for optimization are boundless. So that's good. That's good for me as a researcher.
Yeah, amazing. Well, Matthew, thanks again for joining. Just amazing. Really love learning all about all these things from you, and yeah, just really excited to keep up with the progress of this. It's such an exciting field. Thanks so much.
Thank you. Bye.